Okay, you guys, in this section we're talking about vectors, the goals. Number one, we want to add, subtract, and what we call scalar multiply vectors. Number two, we want to write vectors in component form and ij form. Usually I use a little arrow notation over the ij. And goal number three is to solve applications. I'm going to draw some arrows for you. These arrows ultimately are how we can represent vectors. What do these vectors have in common? Yeah, that's true. They are all parallel. Good observations. How did I draw? Okay, let's call this. So these are arrows, right? They're called vectors, but if you think of them as arrows for now, let's call, just to pick one that's fairly straight, let's pick this one. And let's call this point here the tail of the vector, of the arrow. And let's call the point with the arrow on it the tip. What did I do in each of those arrows to get from the tail to the tip? Okay, or right 2 over 3, either way, right? Oh, yeah. Right 2 up 3 is what I should have said. So, and that's true no matter which one you look at, no matter which tail and no matter which tip you look at, to get from the tail to the tip, you go right 2 and up 3. So, in a very real sense, you guys, these vectors, we don't want to call them equal, because they're not, right? It would be like saying two congruent triangles are equal. Two congruent triangles are not equal. They're different triangles. But congruent means that they're equivalent. The corresponding pieces are the same length or same angle measure. So likewise here, we want to say these vectors, these arrows are equivalent. Okay? I suppose congruent would work, but we don't usually use that unless we're talking about triangles. So in a very real sense, they are congruent. And in I mean, obviously they're not the same. They're all different. But in a very real sense, they're equivalent because to draw them starting from tail and going to tip, you do the same thing, right? So how could we invent some sort of notation to indicate the one kind of vector that all of these green vectors represent? What could we do?
Put them like coordinates?
Yes. But the coordinates would actually be the change in the horizontal value for one coordinate, and then the other coordinate would be the change in the vertical value.
Right.
And one way we represent the change in the horizontal, so if we draw, picking on this vector, if we draw in this right triangle here, then we often represent the change in the horizontal as delta x. The Greek symbol delta looks like a little triangle. X. We think of that as one quantity. And delta x means change in x, or change in the horizontal. And then that's for the horizontal side. And then the vertical side we would call delta y, which means change in y. So the way you're used to thinking of slope, you would say slope is delta y over delta x. That's not quite how we're going to do that here. We're going to represent these vectors as coordinates. But instead of using regular parentheses, we're going to use alligator brackets. The first coordinate we would call delta x. The second coordinate we would call delta y. And this would be a way to represent what we call the component form. So let me tell you what this notation is called. This notation is called the component form of, I do use the word the vector, represented by all these pictures. Okay, so in a very real sense, all these pictures represent the same vector, at least in component form. Okay, now this is not an ordered pair that you necessarily, that it doesn't represent a point that you're used to, right? However, if you plot one vector in particular where the initial point, the tail is 0, 0, then it does turn out that the tip will be delta x, delta y. In fact, in this case, what is delta x, delta y? In this case, how do we represent the vector? Delta x is equal to what? In this case, 2, and delta y is equal to 3. So in this case, delta x is 2, delta y is 3. So we would represent the vector as the, well, ordered pair 2, 3. What is the mathematical definition of a vector then? Well, it is an arrow. It's just what we said it is. But I guess we would call that a directed line segment in math. Now, let's talk for a minute about scalar multiplication. So when you scale something, what do? So if you made a scale model of a car, what are you doing? Yeah, usually it's shrinking, but yeah, stretching or shrinking it, but keeping all of the relative lengths proportional. So scalar multiplication, well, what we want to happen when we multiply a vector by a number, say 2, we would like to make an arrow essentially that's twice as long, headed in the same direction, but twice as long as the original. So let's start with that kind of visual definition as our guide. So let me draw in to kind of convince you of where scalar multiplication comes from symbolically. Let's start geometrically. And let me go ahead and draw an arrow. Okay, so let's say we start with this vector right here. And let's say I want to create a vector that's twice as long. So let's give this vector a name. Let's call it v. And now I want to create a vector 2 times v. And here's what I want to happen. I want to make a vector. So let me use a different color here. Let me use red. I want to create a vector that is, and I'm just doing this visually so it won't be perfect, that goes in the same direction as v, but twice as long. That looks about twice as long. I might be a little off on that, but close enough. So I'm going to say that this vector right here is 2 times v. And you can see they're parallel, so they head in the same direction, right? Yeah. Now, okay, that's all fine visually, right? You can really wrap your brain around that. But what would that mean symbolically? If we represented v with coordinates or components, really, we call these guys the delta x and delta y, we call them components. So, okay, great. Everybody understands that, right? The scalar multiplication. Visually, it's easy. Now, what does that correspond to symbolically when you represent a vector in component form, where its initial point is, say, at 0, 0? Not that it really has to be, but for convenience. So let's say that this vector v, we can represent it with components. Let's just use a and b for simplicity. So instead of using, and you'll see me do this a lot, instead of using delta x and delta y, I'm going to say delta x is a and delta y is b just for convenience. It's easier symbolism. Well, okay. Then how could we get twice v in component form? Okay, those of you that know the answer, what do? You'd multiply a by 2 and you'd multiply b by 2. So the component form would be 2a comma 2b. But some of you have never seen vectors before, so let's give that some justification here based on our visual or geometric definition of scalar multiplication. So I'm going to put this copy of 2v right on top of v. And now I can really adjust it so it looks like it's twice as big. Okay. And I'm going to create, surprise, surprise, a right triangle. Okay, hopefully it's not a surprise. It is trigonometry, after all, that we're studying right now. So I'm going to create 2 right triangles, actually. I'm going to create the one corresponding to, if I dropped a perpendicular from the tip of V, like so. I'm going to create that right triangle. And I'm going to create the right triangle I get when I drop a perpendicular from the tip of 2V. Like so. So that the big triangle that you see, the big right triangle that you see, kind of encompasses the triangle formed by V in the perpendicular and the horizontal side that I drew. And so that this side here is, of course, parallel to this side, because they're both dropping perpendiculars from parallel lines, parallel vectors. Okay. So here's the thing then. In this smaller triangle here, let me zoom in on this. In this smaller triangle here, then this adjacent side to this tip, well, it's really the tail of V. This adjacent side then, according to my labeling, has length A. I'll be consistent with my coloring, so it has length A. And that horizontal side has length A, and the vertical side has length B. And the hypotenuse, now let me move some of this stuff out of the way. Okay, now this hypotenuse then from of just V then has a certain length associated with it as well. And of course you can get that length using the Pythagorean theorem, but let's just give it a name C. The vector that was originally in green, V, is C. Then by the way we've created this geometric definition of scalar multiplication, what's the length of the big hypotenuse for 2V? It's 2C, right? Yeah. So the length of the hypotenuse of the bigger triangle then has just got to be 2C. But we know from geometry that the big triangle, I'll write this down using very very unmathy notation. The big triangle, well, that's a little bit mathy. So the big triangle is similar to the little triangle. What that means is corresponding sides are proportional. And there is a constant of proportionality, which has to be 2. Once you find it for one side, it stays the same for all the sides. The constant of proportionality is 2 and is the same for all sides. That's what it means to be a similar triangle, right? And is the same for all corresponding sides, which simply means then that the horizontal side of the big triangle has to be twice A. And the vertical side of the big triangle has to be twice B. But wait a minute, this is the horizontal component of 2V, the vector 2V. This is the vertical component of the vector 2V. So that's it. I mean, visually we've shown how we should perform scalar multiplication symbolically, right? So the conclusion is this. So component-wise, 2V, it has components 2A and 2B. So then that gives us kind of a guide as to how to proceed generally for the definition of scalar multiplication symbolically. If you have a vector V, and I'll go back to my my component form delta x, delta y here. Hopefully that doesn't bother you. So if you have a component form of V, delta x, delta y, and let C be a scalar. Well, wait a minute. I'm kind of introducing a definition here. Think of a scalar as a single numerical quantity. Okay. Then, this is the big definition we're trying to come up with. C times V, you guys have kind of already told me, has to be What do? You take c times the individual components, delta x and delta y, right? To get the component form of c times v. So it equals c times delta x, comma c times delta y. Does that make sense to you? Not too crazy, right? Okay. Let's suppose you're given a vector v. Then what does, note number one, what does k times v look like? K times v is a vector that is, well, we got to be careful here because we don't know if k is negative or positive, do we? So we're assuming k is a constant. K times v is a vector that is, let's say, absolute value of k times as long as v. And if k is positive, then k times v will point in the same direction as v. And if k is negative, it'll point 180 degrees from that. It'll be point in the opposite direction. So we'll make the first note that k times v has length absolute value of k times that of v. Does that sentence make sense to you? K times v has length absolute value of k times that of v, the length of v, in other words. And then we should say this. If k is greater than 0, k times v points in the same direction as v. And note number 3, if k is less than 0, then it points in the opposite direction. Then k times v points in the opposite direction as v. Let's let u equal the vector 2, 1, and v equal the vector 1, 4. Find u plus v. Now, if you wanted to, you could assume that u is at the origin, the tail anyway. But here, when you're talking about addition or subtraction of vectors, that's not necessary. So I'm just going to pick a random spot to draw u. And then I'll show you how to visually add v, and then I'll show you what it means symbolically. And it actually won't take that long. So let's just start, for the sake of argument, let's start with the tail of u right here. And it's at the point 2, 1, but I don't even care. Doesn't even matter. And so you treat the tail of u when you're drawing the vector, wherever it's at, you treat that like the origin. So you're going to go from that tail, you're going to go right 2 and up 1. So does that make sense how I got my visual representation of u? And again, I picked that tail randomly. If I had started over here, I would have gone from that tail over 2 up 1, and it would have been an equivalent vector, just a copy of the other vector, right? So forces add vectorially, so do velocities and other quantities add vectorially. So here's what I mean by adding vectorially. So you take the vector u, if you want to represent it using a picture, which is the vector 2, 1, I'll put that right here. And on its tip, which is where the arrow is, right, where this part of the arrow is, on its tip, you make that the tail of v, the thing you're adding on. So let me do that in blue. Now let me do it in red so it shows up better. There. And then, so that's the tail of v, and then I'm going to draw v in. So what do I do from that red point? So where do I go? Right 1 and up 4. So over 1 and up 1, 2, 3, 4. And that's going to be the tip of v, like so. And then it turns out you get u plus v by drawing an arrow from the tail of u to the tip of v. So look at the vector in green, look at its beginning point, the tail, and draw an arrow from that to the tip of the vector in red. And that is u plus v, everyone. So the vector in blue is u plus v. And that is how we add vectors using the triangle law. There's also a parallelogram law, and where u plus v turns out to be one of the diagonals of a corresponding parallelogram, but we're not going to worry about that here. The triangle law is good enough for most purposes. So that's how it's done, and that's how, for instance, forces, if you represent a force by the length of the vector, so that's weird, like a force in pounds would be represented by the length of the arrow. But it actually works out quite well in modeling real-life situations where if you use arrows, and the length of arrows represents the amount of force, so the longer the arrow, the more force. It turns out that forces applied to an object at different angles add vectorially. Imagine two people kicking a soccer ball at the same time. One person from over here, one person from over here. Where does the ball go, right? That sort of thing. Now, let's say we wanted to take u and subtract v. Oh, so I guess I can, well, let me use one down here. Let me draw another one down here. Let me draw u again. So I'm going to make my tail right here and go over 2, up 1. So there's another copy of u, and I'll do the subtraction on this guy. Now, we know the component form of v, so what is negative v? Negative v is, it's just what you think it is. It's -1, a scalar of -1 times v, which would be -1, -4. So all I have to do is think of u minus v as u plus a negative v, and use the triangle law once again to do that addition. And that'll be u minus v. So, okay, what I do is I take the tail of negative v and put it on the tip of u. So I'll do that in red right here. And then from there, I go left 1 and down 4. Does that make sense? So left, let me get the right color here. Left 1 and down 1, 2, 3, 4. And notice it will look like an exact copy of what we have over here, except headed in the opposite direction. So let's be clear here. This is negative v here, whereas this was positive v right there, and in green this was u. And this is still a copy of u. So then remember what we did in the first one with u plus v. We connected the tail of u to the tip of v. We're going to do the same thing here, except it's the tail of u to the tip of negative v. And there you go. There's u minus v. So actually, I wanted to use this first drawing for something to convince you of how we add in component form symbolically. So let's use that drawing to convince you of how we add symbolically in component form. So for a second, let me go ahead and erase that guy. It's going to get in the way. Let me erase that guy. So let's examine u plus v here. And I think that'll give us a clue. So this vector in blue, what would, so notice the tip is right there. What would the change in x be, delta x, from tail to tip of the vector in blue? Just count. 1, 2, 3. Delta x is equal to 3. And then what's the change in the y coordinate? What's delta y from tail to tip? Looks like 1, 2, 3, 4, 5. Delta y is 5. Okay. Now compare that with the original vectors u and v. And what are we essentially doing? So first of all, in case I'm not clear here, u plus v in component form then is 3 comma 5, right? Okay. That's what I'm saying. So essentially what we're doing to get the component form of u plus v, what we're doing symbolically is just adding corresponding components, aren't we? Of u and v. So you add the 2 and the 1, you get 3. You add the 1 and the 4, you get 5. So, well, that's about as simple as you could hope for, right? So we can state that rule now. Let's do it. Let's state that rule symbolically. I need to define symbolically the vectors. So just to switch things up once again now, I'll let v equal, instead of ab, I'm going to call the components v1 and v2. And I'll actually state u first because I like alphabetical order, I suppose. And I'm going to let u equal, or have the components u1. So this is a subscript 1, u2. So it's just a way to generically, symbolically define u and v. Then you guys tell me, what's u plus v? Yeah, then u plus v, this is the symbolic definition, you guys. So you said u1 plus v1 for the first component, right? u1 plus v1, comma, u2 plus v2. So that's the symbolic way of saying what we just said, or what we just observed, actually. Okay, so that's a definition right there, isn't it? That's the definition of addition of two vectors, component-wise, right? So now we're ready to perform these symbolic operations. Again, I don't know if I've already said it or not. In the homework, unless you're told otherwise, assume that the tail is 0, 0. Okay, and the reason I say that is most books will do that. So if it shouldn't be an issue actually when you're just adding these things together, but a lot of books will think of it that way, and it's a little bit restrictive because in physics you like to put copies of vectors in different places, like you saw when we added geometrically. But okay, so we're in this example we're going to let v equal the vector 2, 3 in component form, and u equal the vector -3, -4. Perform the following operations: v plus u. So what's v? V is 2, 3, and u is -3, -4. And so we're going to add these guys together. So what do we get? Yeah, and just for completeness in the notes, I'm gonna write for the first component 2 plus -3. But obviously you can do that in your head, and you don't have to show that work if you don't want to. And then what's the other one? 3 plus -4, or 3 minus 4. If you do want to show the work, you could just write it as 3 minus 4. So what does that turn out to be? -1, -1? Oh, that was an accident. Okay. Yeah, I just made up the example. I didn't mean for them to both be the same. They won't always be the same. Okay, now v minus u. Okay, so let me take a copy of what I just wrote down. So in the last problem, this is what I wrote down, so this first guy 2, 3 was v, and the second guy -3, -4 was u. But what am I going to change here? Just the plus to a minus. Now, you can define subtraction using addition, right? So what does this become if you want to write it using addition and in component form before you combine it? It'd be plus what? Well, here, you could think of it like this. Plus a scalar of -1 times that vector, -3, -4, right? And so if you do that, these guys change, the signs change in both of these. They both were negative, so they change to positive. Does that make sense? Okay, easy enough. You add them together, what do you get? 5 and 7. That's it. You thought it was going to be harder than that, didn't you? Okay, so I want to remind you, u was -3, -4. So 2u, in part C we're finding 2u, which would be 2 times -3, -4. Okay, so what's that? Yeah, so maybe for variety we should do something other than 2, right? What do you want to do? No, I don't want to do that. How about -5? So what would what's the scalar? This is scalar multiplication. What's the scalar? -5. So u was -3, -4, so we're going to multiply that times -5, and what would the result be? 15, 20. Okay. Questions on that? That's it. Oh, well, here it gets a little bit interesting, at least. We're combining operations in this one. Okay, think back to order of operations. Do you think that's going to change much? So let me ask you this. Are we going to scalar multiply first or add first? Scalar multiply first. So let's write down what it is. I think u was -3, -4. Let me double check. And what was v? So 2, 3, and -3, -4. So when you see 2u plus 3v, it means 2 times u, which was -3, -4, plus 3, a scalar of 3, times v, which was 2, 3. Do the scalar multiplication first. What is 2 times -3, -4? What vector is that? -6, -8, plus, what's this vector? 6, 9. Now you add component-wise, add corresponding components. What do you get? 0, 1. Any questions? Yes?
So on our tests or on like the homework, when you tell us to add two vectors and you're showing a picture, do we have to like move one of the vectors over like you've done, or can we just add them?
There won't be a whole lot of problems where you're adding geometrically.
Okay.
But there might be in a physics class. So if you're given two vectors, there's one, and let's say this is another one, and you want to add them geometrically, the best way to do it is to get some tissue paper and copy. But if you just want to do it by hand and estimate, then what you would do is you would, and it really doesn't matter, by the way, if you take u plus v or v plus u geometrically, even though you'll get a different triangle, the side you connect from tail to tip will be the same vector in the same direction. So it'll be the same vector equivalent anyway. So what you would do then is you would take, say you want to add the vector in green to the vector in red, then you would take a copy of the vector in red, and you could just eyeball it, right? That's pretty close. And then the vector in black right there that connects the tail of the vector in green to the tip of the vector in red would be the sum. So if this is u and the vector in green is v, then the vector in black would be u plus v. And I'll say one more thing about that. If we had then a vector u and a vector v, what if we wanted to take, let's go with the other order now. How about v plus 2u? Now you guys tell me, geometrically then, that's what we're doing, geometric addition, which is important. How would we do this? What should you do first? Should you double the size, the length of u, or should you try to add first and then do something with the 2? What makes sense?
Double the length.
Double the length of u, and then do the addition as usual, right? So I'm going to double the length of u, and again, I'm just going to eyeball it. I'm going to say that 2u probably looks something like that. Would you buy that? And then I'd have to draw, if I weren't using technology, I'd have to draw another copy of that, but I am using technology. So I'm going to, if I want to find v plus 2u, I attach to the tip of v the tail of 2u. Let me move this down. And then to get the actual vector v plus 2u, I connect the tail of the first vector to the tip of the second vector in the addition. So there you go, v plus 2u.